better check with Wen Zhuang before she starts, okay? But Sangeeta's fine. Right, good. Carry on, Sangeeta. Sorry to interrupt.
Yeah, sure. Yeah, no problem. Thanks, Susie. So today the focus of my talk will be to understand how titanium fine-tunes the microstructural aspects of NV3S and superconducting phase, which in turn can influence the critical current density. So in this talk, I won't show much of the superconducting properties. Rather, the talk will emphasize more on the probing microstructural features, which alters the JC and the upper critical field. So before I delve into the titanium role, I will first explain how the NB3SN forms in a bronze method, which is one of the commonly used technique in the industrial scale. So in the bronze method, the niobium rods are inserted in the bronze ingot and the entire assembly is then drawn as a wire. And this assembly is subjected to annealing process in the temperatures typically in the range of 650 to 800 degrees Celsius in the time zone of 225 hours, which is a very long annealing time. And you could see in the figure as I have shown that the NB3SN phase forms surrounding each of these niobium filaments. So the performance of the bronze processed NB3SN wires depends on how well this NB3SN phase is formed, whether it has pores, it doesn't have pores, or how is the grain structures and all. So one of the most important aspects of bronze processed NB3SN phase that has formed using this technique is the presence of Kirkendall voids, which you can see as the dark dots I've shown by red arrows. Since these voids are at the interface of copper tin NB3SN, this suggests that tin is the fastest diffusing species during the growth of NB3SN. Now, this is a bit discrepant because when we look at the crystal structure of NB3SN, which has an A15 ordered structure, you could see on the left side, I have shown the nearest neighbor bonds of tin. So tin is surrounded by 12 niobium atoms. And so there is no availability of tin-tin bonds. So tin can move via lattice and only if there are stable anti-side defects present in the crystal structure. On the other hand, the major component of NB3SN, which is niobium, has 10 niobium atoms as its surroundings and 4 tin atoms, which means there is the presence of niobium bonds, and if there are vacancies present in the structure, niobium can easily diffuse by its own sublattice and help forming in the NB3SN. So why it is so that during the experiments we see tin is the only mobile species and niobium is not. So now we'll see how and why at all tin moves and helps in the formation of NB3SN. For this, we have diffusion coupled a pure niobium piece and a pure copper tin piece, and then annealed in the similar temperature and time zones and as it is followed in the case of bronze process. And there are three key aspects or three key observations we have made. Firstly, it has a parabolic growth type, which means when you plot layer thickness of NB3SN versus the annealing time, it follows a straight line. So it shows that the formation of NB3SN is a diffusion control process. Unlike it is limited by the diffusion process and not by the reaction. So tin can easily react with niobium, but it gets limited because of the diffusion process. And secondly, with an increase in the tin content from 7 to 8 atomic percentage tin, you could see that the growth kinetics have increased. The growth kinetics has increased. And thirdly, there is a presence of Kirkendall plane at the interface of NB3SN and copper tin. This Kirkendall plane is envisaged with the usage of titania particles, which are very unreactive with both niobium and copper tin. So during the reaction, what happens is, since these are very unreactive, it gets trapped in a particular plane depending on the relative mobility of the species. And since it is trapped in between niobium tin and copper tin, we could say that tin is indeed the fastest diffusing species. So either kinetic factor could drive or the thermodynamic factor could drive or accelerate the kinetics of NB3SN. So when we looked at the grain structure, there was indeed no change. So we thought of why not to see the thermodynamic driving forces, or rather the chemical potential gradient, what we call in terms of dynamics. So we could see that the chemical potential of tin decreases while moving from copper tin to niobium side. So you could see in the right side of the figure where I have shown the change in driving force with the variation of 10 atomic percentage. So let us assume only 8 atomic percentage. You could see the driving force is negative, which means the chemical potential is negative. So your free energy is decreasing. So tin has a driving force to diffuse, while for niobium it was positive. So that is the reason why only tin plays a major role in the growth of Nb3Sn, and niobium does not have any role when it is copper tin niobium system, which is basically the bronze process. So now we observe that although with an increase of 10% in bronze, there was absolutely no change in the critical current density. That was because there was no refinement or no change occurring within the Nb3Sn grains. So over the years, many people have attempted to enhance the high fill performance of Nb3Sn wires by the alloying approach. So what they did was to alloy with certain small amount of different alloying elements. And among many such alloying elements, titanium has emerged as one of the potential candidates, which when added even in quantity as small as 0.5 atomic percentage, could enhance significantly both the upper critical field, which is BC2, and the critical current density. Here I have shown in the plot, just for the comparison, how doping with titanium enhances the high field performance, usually in the 7 to 8 Tesla range in comparison to zirconium. So that's why we have chosen the alloying element titanium for our study. Secondly, in such bronze process techniques, there are two ways: internal doping and external doping. Internal doping is when you dope or alloy titanium in niobium, and external when you dope titanium in bronze. And most of these studies, or most of the times, we see that we deal with the either mono or multifilamentary wires. So for making of the wires, these wires are subjected to certain degree of deformation, and during deformation you tend to introduce many mechanical strains into it. So with the introduction of strains, this can in certain extent influence your growth kinetics of Nb3Sn. So to eliminate the influence of deformation processes, we have implemented a different approach to understand the role of titanium. In this case, we have implemented diffusion coupled approach. So now what is diffusion coupled approach? In this approach, you join two dissimilar materials. So in this case, we are joining bronze with niobium and then annealing it at a certain temperature and time. And these alloys we have prepared in-house in such a way that we could alloy with titanium both this bronze and niobium separately, but in a systematic manner. What do I mean by systematic manner? It means like I add 0.2 atomic percentage of titanium and then 0.5 atomic percentage titanium in bronze. And in case of niobium, I add slightly higher amount of titanium, which is 2 and 3. So in case of niobium, I have added higher percentages of titanium because the JC doesn't change much when it was below 1 atomic percentage titanium. So now we'll see how actually titanium influences the various factors. So you see, in case of titanium-free Nb3Sn, it was only the layer thickness was only 14 microns, which is on the very left-hand side. And with the addition of titanium to both niobium as well as bronze, there is a tremendous increase in the growth kinetics. It has increased by almost 4 to 5 times. You could see that when niobium 3 titanium is there, it is 73 microns, and when it is 0.5 titanium percentage in bronze, it increased to almost 88 microns, which is almost like 5.5 times. So, and also the critical marker plane was again noticed exactly at the interface of bronze and Nb3Sn, which means even with the addition of titanium, your tin remains the faster diffusing species, and it is an important component in the growth of Nb3Sn. And secondly, with an increase in the growth kinetics of Nb3Sn, the activation energy for Nb3Sn growth also decreases. So you could say in the right hand side, I've shown the activation energy plots where the activation energy has reduced from 514 kilojoule per mole in case of titanium free Nb3Sn to almost like 200 kilojoule per mole. So there's a decrement of almost like 300 kilojoule per mole with the titanium addition. And another interesting feature are the dark contrasted features, which you could see in the lower part of the micrographs, you could see it is embedded within the NB3SN matrix. So since the size of these dark contrasted features were very nanometer in size, we tried to probe the microchemistry and the crystal structure of it, or rather what could be these precipitates, using the transmission electron microscope. So what we saw that the dark contrasted features were very much rich in titanium, as you could see in the composition plot, where niobium, tin, and titanium in red color. So titanium has a huge spike when we conducted a line scan across one such precipitate, and there is a depletion of both tin to a certain extent and niobium. And when we captured the diffraction pattern from one such precipitate, we found that it crystallizes in the beta phase. So matching the composition and the crystal structure, we could say that these precipitates are beta niobium titanium phase. Although in the case of titanium addition to niobium, we could not see any precipitate at first hand, but since the growth kinetics increased, we thought it is not a very bad idea to just make an FIB sample and see the TM. So then we noticed that there was indeed the presence of similar kind of precipitates at the triple junctions of NB3SN phases, and it has the similar composition of titanium as well as niobium. So one important factor what I would like to draw your attention to is that the location of these precipitates. You could see these precipitates are located exactly at the grain boundaries of NB3SN. Since these are present at the NB3SN grain boundaries, we have a question like, do these precipitates have any role in the grain refinement of NB3SN? So to quantify this, we examined with electron backscatter diffraction tool, which is commonly known as EBSD method. You could see that in the case of titanium free samples, the grains are in the range of almost 4 to 5 microns, and a very large area was covered by the bigger grains. And as we increase the titanium percentage, firstly the grain size distribution becomes narrower, and a higher percentage is covered by smaller grains within like 900 nanometer to 1 micron. And since there was a higher volume fraction of titanium rich precipitate in the case of titanium addition in bronze, we could see that the grain size distribution was much lower in the case of 0.5 titanium percentage. And we could say that these precipitates are actually retarding the grain growth. They are pinning down the grain boundaries, and by the Zener pinning mechanism, it restricts the grain growth of NB3SN, which means the grain boundaries of NB3SN will be much higher in comparison to titanium free samples. And the presence of higher amount of grain boundaries have two uses. Firstly, one advantage is it facilitates the diffusion flux of tin along the grain boundaries and increases the growth kinetics of NB3SN. And secondly, as we know, the critical current density follows an inverse relationship with the grain size. So the critical current density will be much higher when titanium is added to bronze. So I'll show the JC plot at the end of the presentation. So the grain boundaries, which were devoid of precipitates, we examined using the atom probe tomography just to see if the stoichiometry of NB3SN remained intact even at across the boundaries. So you could see there is a bright field image of APT, and there lies a grain boundary which is shared between two misoriented grains, and we constructed an iso composition surface of a value of 5 atomic % copper. And there was indeed a copper enrichment at these boundaries, which is represented by the blue color. And when we conducted a line scan across one such grain boundary, we found that there was a copper segregation within a range of 2 to 5 nanometer. And secondly, there was a dip in the niobium percentage. So niobium from 70, it decreased to almost about 10 to 20 atomic percentage. So you could say that since the tin composition was almost same throughout the grain boundary or across the grain boundary, so in the NB3SN case, the copper atoms actually replace the niobium atoms. So the moment this replacement happens, there is a stoichiometry change happening for the NB3SN phase. So such a compositional inhomogeneity, which spans for over 2 to 5 nanometer, may also help pinning the flux lines. Now we have understood like how tin dissociates from bronze, which is copper tin, and reacts with niobium substrate and forms NB3SN. Since NB3SN nucleates on the niobium substrate, there's a question like, can the orientation of niobium influence the texture evolution of NB3SN? Because you see, since NB3SN is A15 structure, it may have certain amount extent of anisotropy in the JC properties. So it is important to understand how the texture evolves. So in the case of titanium-free NB3SN, it rather displayed very weak random texture, random crystallographic texture. So in the absence of titanium, in the absence of any precipitate, what happens is the nuclei of this NB3SN phase could have all possible sorts of orientation. So how can you identify different orientations? Since within the NB3SN phase, the color codes are very much different. These different colors represent different orientations of NB3SN. So you could see red, violet. So there is nothing such typical color codes. So the orientation effect is very weak. This is in contrast to the titanium added samples, where you see the layer is not only strongly textured but also follows exactly the same orientation as that of its adjacent niobium substrate. For example, in the top figure, where titanium is added to niobium, you could see niobium 3 titanium I have written. So there are two pole figures on left and right hand side. So left hand side pole figure corresponds to the NB3SN product phase, and the right side pole figure corresponds to the niobium substrate, which is your parent phase. In this case, it is niobium, pure niobium, and the niobium with titanium addition. And there are certain poles, which mean this denotes the orientation. So you could see the location of the poles in the case of both left and right hand side pole figure are almost similar, and also the pole density are almost same. That is because the niobium titanium we are considering statistically very few grains, while the NB3SN there are many grains for only one particular single niobium crystal. So the mechanism for the evolution of such a strong texture we can understand if we follow the oriented nucleation type. So what is oriented nucleation mechanism? So oriented nucleation says that since there are beta phase in the form of precipitate, it allows the nucleation of only those orientations which lies very close to that of its niobium substrate. And why it allows like that? Because if it does like that, then it reduces the energy, grain boundary energy, by nucleating the closer orientations. So, and even during the growth, the orientation remains the same as that of its nucleated NB3SN. So we were lucky to have locate the trace of high angle grain boundary for one of such niobium grain, and you could see that the grains of the NB3SN phase acquires a similar orientation the moment when there is a change in the orientation of the niobium grain. For example, in the right hand side figure, you could see there are two different niobium grains, and the phase, the NB3SN phase that has formed adjacent to those grains have orientations or the color coding exactly to that of the niobium substrate. So we could say that with the addition of titanium, not only the NB3SN kinetics increased, but also we find a strong crystallographic texture for the product NB3SN phase. So with this, I would like to conclude my talk. So with the addition of titanium in both niobium and bronze, we see a significant enhancement in the growth kinetics of NB3SN phase. That is because we attribute to the small scale titanium rich beta titanium niobium precipitates, which we find at the grain boundaries, and because of the grain refinement, it facilitates the higher diffusion flux for tin. And when titanium is added to bronze, even if it is in minute quantity in comparison to titanium alloying in niobium, there is a larger fraction of smaller Nb3Sn grains because of higher volume fraction of beta titanium precipitates. And also, if you carefully see the morphology of beta titanium niobium precipitates in case of copper tin titanium, these are completely covered the grain boundaries and very much disoriented in the directions. And there is a strongly textured titanium containing Nb3Sn layer, which exhibits a unique pattern with the orientation of periniobium grain. So in the bottom right corner, you could see a JC plot where you see that when titanium was added to copper tin, it has higher critical current density in comparison to the titanium addition to the niobium. So the key take-home message is that the alloying of titanium in bronze is more effective when it is added in niobium for the bronze processed Nb3Sn wires. So thank you.